Yeah. This is the perspective view of the midpoint of CD with respect to the vanishing point B. So B is the point on the horizon. So I should use blue because blue is from the horizon. So I have C, D, B. I choose any horizon. You know, it doesn't matter which horizon. And then the midpoint in perspective. So it's here it lies closer to D than to C. This is called the fourth harmonic of B with respect to C. Yep. And this is called a harmonic quadrupole, or you also say that the two pairs separate each other harmonically. It's really a property of two pairs. Because if I swap B and A, the cross ratio is still -1. If I swap C and D, I have the same perspective midpoint. Yeah? If I interchange AB and CD, both, it's also harmonic. So for example, as I mentioned before, D is also the midpoint of AB with respect to C. So it's really a property of two pairs, two unordered pairs. So that's fourth harmonic, interior, exterior of the conic. Yep. So maybe we should look at interior, exterior. So start with a simple example. I have two components. Which component is the interior? Which component is the exterior? One is interior. Very good. Another example. I have a parabola. Which is the interior? Which is the exterior? Yeah, one is the interior. Now the most difficult case, I think. Hyperbola. 1, 2, 3. Oh, 3. That's strange. What is the interior? What's the exterior?
1 and 3. 1 and 3 is interior.
They belong together.
1 and 3.
Yeah?
1 and 3 interior.
1 and 3 is interior. Okay. And if you think they are glued together at infinity, so they form one disk.
Yeah. But what is the meaning of interior and exterior?
Yeah.
Why is it important
Okay.
Interesting.
or interesting?
Okay.
Or not.
Well, first, what's the meaning? We have seen that if you cut a projective plane along a conic, an interesting conic, then the plane decomposes into two parts which are not equivalent. One is a disk, the other is a Möbius strip. Yeah? And by definition, the disk is the interior, the Möbius strip is the exterior. So this has the topology of a disk, the exterior has the topology of a Möbius strip. This is orientable, this is not orientable. The same here. Okay. That's one way of describing it. There is another way. It's in fact a projective notion. Here you have the property, if you have a point in the interior, then any line passing through this point intersects the conic in 2 points. The same is true here because this is a projective statement. So if it's true in one case, it has to be true in all cases. And here too, in the interior, all projective lines intersect the conic in 2 points. On the other hand, if I have a point in the exterior, then there are lines which do not intersect at all. And there are lines, in fact exactly 2, which are tangent. And other lines intersect in 2 points. So all 3 cases occur. 0, 1, or 2 points. And the same happens here. 3 types of lines. You see? And the same should happen here. and of course lines which do not intersect like this. Yeah? Okay. Now why is this important? It's really rather a nuisance. It's something like things would be easier if there wasn't a difference between the interior and the exterior. So it is important, it's a notion which is preserved by any projective transformation. Projective transformations are about, they represent kind of the highest degree of freedom we have in this subject. But even if you apply any projective transformation to this, the interior is always mapped to the interior, and the exterior is always mapped to the exterior. So whatever, I can do lots of things to this ellipse. I can make a parabola out of it. I can make a hyperbola out of it by choosing a special line at infinity. I can even make it a circle. I can force certain lines to be parallel. I can make life really easy. But something which I can never achieve by any projective transformation is to make an exterior point out of an interior point. Yeah? Okay. And that means that, for example, if you're talking about polar lines, you remember polar lines? I have a conic, I have a point outside, I take two tangents, and then this is the polar line, lowercase p of capital P, of the point P. Now, so this is easy if P is an exterior point. It's less easy if P is an interior point. Or, for example, suppose we do it the other way around. So usually, to avoid this, I formulate things the other way around. I say, well, we have 2 points, A and B on the conic. I take the 2 tangents, which are, of course, lowercase a and lowercase b. Yeah, because the polar line of a point on the conic is the tangent line. Yeah? Okay. And then, for example, what a statement we could consider this statement: given a conic, given 2 points on the conic, distinct points, take their tangents, they intersect. Projective geometry, lines always intersect. This point is always in the exterior. Yeah? This is just a claim. I don't say it's true at this moment. It is true, but it's just a claim. It's a mathematical statement. It's a projective statement. All notions occurring in it are projective. I talk about conic. I talk about points on a conic, tangent, intersection point, and exterior, which is also projective. So to prove this, I only have to prove it for a circle, and in that case it's true. So this is also true for hyperbolas. This is also true for parabolas. Yeah. So it's important to know as many projective notions as you know, because you know that they are very robust notions. You can do almost anything you like with them, and they do not change. Yeah. Okay, we've talked about projective notions, affine notions. There are 2 ways to approaching an affine notion. I have these 2 points. This is the most constructive one. You actually define it in terms of the primitive affine structure, which is projective notions and the line at infinity. So, of course, any projective notion is certainly an affine notion. It's coarser. Projective geometry is coarser than affine geometry. So, any projective geometry is any projective notion is an affine notion. And the only new thing in affine geometry is the line at infinity. So, a standard example is, of course, the notion of parallel lines. Lines intersecting at this line of infinity. That's an affine notion. A typical example. And midpoint. Midpoint, we had that example. Midpoint is the 4th harmonic with respect to the point of infinity. Or the difference between ellipse, parabola, and hyperbola. That's an affine notion. The number of points at infinity. Yeah? Okay. So that's the kind of the constructive way of showing that something is affine, by actually defining it in an obviously affine way.
But the fourth harmonic itself isn't
Harmonic.
That's
Yeah,
the
the fourth
projective
harmonic.
notion, isn't it?
Yeah, but any projective notion is certainly affine.
Yeah, okay.
Because it's, so it's certainly affine, it's even projective.
Yeah.
Okay. Yeah. Another way to show that something is affine is to show that if you have a certain notion, you can apply any affine transformation to it, and this notion is preserved by this transformation. Do I have an example? Yeah, I do, but they're too complicated. Okay. Did we have any example during the lectures of that? Of this number 22?
Then ellipse stays an ellipse or something like
Yeah, we can do that this way, also this way. That's easier. Well, I do have a problem myself, which is showing that something is projective, because I know that it is invariant under. Oh yeah, I can give this example. Let's return to this interior-exterior business. Yeah. We noted that for me it was a surprise. The interior is a disk, the exterior is a Möbius strip. So no projective transformation can map the interior to the exterior, because any projective transformation is continuous. Not even a continuous transformation can map interior to exterior, because it's a topological notion. Okay. So I know that this notion of interior-exterior has to be projective, because it is preserved by all projective transformations. But can I find a projective characterization? Yes, we can, in terms of points and lines and intersecting points. It's in fact a notion of incidence geometry. And I discovered this. First I know that it's invariant under transformations. And then I thought, well, then maybe I can give another kind of characterization of interior and exterior in terms of points and lines and incidence. And you can. But I do not have an example for affine geometry at this moment. So maybe it's not so important.
Maybe we'll find one.
Oh, something. Oh, yeah. Okay, yeah. Thank you very much. Thank you very much. I didn't read it properly. Showing that something, that's important. Showing that something is not affine by showing that it is not invariant. Well, we did that. So look, for example, at the notion of a right angle. Right? Yeah. Orthogonal lines. If you can find one right angle in the Euclidean plane and one affine transformation which does not map the right angle to a right angle, then you have shown that this is not an affine notion. And you can never define it only using projective terms and aligning infinity, because it's, thank you, it's a negative version.
It's a logic statement like if not invariant, then not affine.
Exactly.
That's the statement. That shows.
So for example, once I was playing around, I was thinking maybe there is a kind of geometry between affine geometry and similarity geometry. Similarity geometry is 4 degrees of freedom, affine geometry is 6. Maybe there is a 5-dimensional geometry in between. In affine geometry, I only have the notion of parallel lines, but not of angles. So I only have an angle of 0 degrees, you could say, yeah? Parallel. In similarity geometry, I have any angle. And I was playing around, maybe I can have a kind of geometry in between where you have the notion of parallel and perpendicular, but nothing in between. So I was looking at all affine transformations which respect the notion of right angle. And then I discovered you get all similarity transformations. So if I have a right angle, I have all angles. And then afterwards I thought, yeah, it's obvious.